Hello everyone and welcome to a video lecture of chapter 20. Okay, so there are two questions here. The first one, he says, how much total charge passed in 4 minutes? How much total charge passed in 4 minutes? Okay, and then part B, it says, how many electrons would this how many electrons would this be? Okay, so let's answer the first part. He says how much total charge. I think we've done that before. We have here we know that the current is delta Q over delta T. So how many total charges? So basically, you're looking for delta Q or Q. That will be I delta T or delta Q. And in this case, we have the current is 2.5. Multiply this by delta T. That's 4 minutes. Of course, convert it to seconds. So that's times 60 seconds. And then we would calculate that, and that would be what is that? This is 240, so that's 2.5 times 240, and that gives me 600 coulomb. Okay, that's a lot of coulombs. Okay, now part B, it says how many electrons would this be? So what is that? How do we do that? Well, we know that the number of electrons times the fundamental charge, it gives me the charge. Is that right? We've done this formula before. We've dealt with it. So he's looking for n sub e. So n sub e in this case, the the charge divided by the fundamental charge. Well, the charge is 600 divided by the fundamental charge, which is 1.602 times 10 to the negative 19. And we calculate that. I have it in front of me. 3.8 times 10 to the 21 electrons. Okay, there we go. Simple. Okay. The next topic. So far we have covered those two topics: the electron current and electric current I. The next topic is Ohm's law. Ohm's law basically said it's more of an empirical law, and it's equal to, he said that the voltage is equal to IR, the electric current times the resistance. Okay, and when we say resistance, I don't know if I said this in class or not. When we think about resistance, yes, there is a device, a little object called resistance, but the best way to think of a resistance or resistor, think of a light bulb, or for example a heater, or your stove, for example, the top of your stove, and so on. Okay, these are all examples of a resistor. I mean, for example, how does a light bulb work? Well, the light bulb is nothing but a resistor. The light bulb, you have this small wire. It looks something like, let me draw it. So it looks something like that. And inside here you have this wire, which is tungsten wire, like that. Okay, I believe this part here is positive, and the body of this thing is negative. So when you connect it to voltage, let's say you connect it to a voltage here, let's say 120 volt, like the volt that you have in your home, and then what will happen? A huge current will pass through it, and there is so much current going through this little wire here. It's this tungsten wire, because it's very, very thin. So what will happen? It will resist the flow of the current. It will resist the flow of those electrons due to this high voltage. As a result of that, it will heat up. It will heat up so much it will glow. Okay. So what does the resistor do? Well, it resists the flow. See, if it allows it to flow smoothly, nothing will happen. It will just stay cold. You can actually put your finger in here and touch it. Nothing will happen. but it resists the flow of the current because the wire here is extremely thin, okay, and that is the cross-sectional area is very, very low, and you got this huge number of electrons coming through. So it's like imagine a small, say a garden hose, and you connect it to a fire truck. It's not designed for that. It will explode. They just have this huge gush of water coming through a garden hose. It will not be able to take it. It's not designed for that. You see, this is the same way. So what will happen is that it will resist the flow because there's just so much electron going through it. It will heat up so much it glows, and that's basically how you get the light. Same thing with the heater. Same thing. The heater, you get that piece of what do you call it, ceramic, and then you get this wrap. I'm talking about the classic heater. You get this wire wrapped around it like that, if you remember, something like that. And then here is one end, and one end is positive, negative, and then it resists the flow of it, and this resistance to the flow, it causes it to heat up, and of course it will give off heat. That's the same thing with your stove, especially I'm talking here the electric stove. Got that coil thing there, especially in the rented apartments, and when you turn on the heat, this thing glows. You can put your pot on top of it. Same thing. It is a bad conductor or a good resistor, and it resists the flow, and as a result of that, it heats up. Okay, so basically that's what a resistor is. That's one way to see it. Okay, so anyway, Ohm's law says you get the voltage is equal to the current times the resistor. It's one of the most fundamental laws of electricity, just like F equals ma for mechanics. This is a very, very fundamental law. And the interesting thing about it is an empirical law. In other words, you cannot derive it from first principles. It is an empirical law. I'll give you an example and show you what that means. Oh, before I do that, let me talk about the units here. So we said that Ohm's law says V equals IR. So R is V over I. So what's the unit here? Well, the unit of volt is voltage. Excuse me, the unit of voltage is volt, and the unit of the current is amp, so it is volt per amp. Okay, we call this the ohms. Okay, ohm, and it has the symbol, the Greek letter omega. Okay, so that's basically what it is. Here's an example. He said we have a flashlight bulb, that is, resistor. In other words, the the bulb itself plays the role of the resistor. So we have a flash bulb resistor. Let's say that the flashlight draws 300 milliamp of current from a 1.5 volt battery. Now, what's a 1.5 volt? It's basically one of those AA batteries. Okay, all the AA or AAA, each battery has 1.5 volts. So think of it like imagine you have a light bulb that works only one single, say, AA battery, and that AA battery has a 1.5, and then it gives off a current of 300 milliamp, which is 0.3. Is that right? 1, 2, 3. Yeah, 0.3 amp to this light bulb. It lights it up. Okay. And then there are two parts. The first part, he says, what is the resistor? Okay, and then the second part, it says if the battery becomes weak, and voltage drops to 1.2 volt. The screens behind me are playing around because I'm not activating them. Anyway, so if it says if the battery becomes weak and the voltage drops to 1.2 volt, how would the current change? How would current change? Okay, simple problem. I promise we'll do something a little bit tougher later on. So for part A here, the resistor, we know that Ohm's law is V equals IR, so therefore R is equal to V over I, and the voltage is 1.5 divided by I is 300 times 10 to the negative 3, and we calculate that, and the resistor becomes equal to 5 ohm. Okay, so R is equal to 5 ohms. Got it? Part B, very simple. He said if the battery becomes weak and voltage drops to, so we have the new voltage is 1.2, and the resistor is still the same. R is 5 ohm. He didn't say anything about that. And how would the current change? And usually when batteries gets older, you have an internal resistor that increases, so that affects the resistors. But anyway, we're ignoring that. So what would be the current? So the current would be volt over the resistance, so that's 1.2 volt divided by 5 ohms, and that's equal to 240 milliamp. As you can see, as the voltage drops, also the current drops from 300 to 240. Got it? Okay. Okay, and two more short topics. I'll go over them, then we'll do some problems. The next topic is the concept of resistivity. Resistivity. Let me activate Pearson. Oh, it will come out hopefully in the background. Okay, so what is the resistivity? Are we on the back same page? Yeah. Okay. What is resistivity? Well, so we dealt with the term resistance, R. Okay, and resistance. If you ask the question, what does resistance depend on? Resistance depends on. It depends as far as the wire is concerned. Resistance of a wire or a conductor. When we say conductor, it means a wire. What does it depend on? Well, okay, let's see. If I have a wire and if I make it longer, here's a wire of some length L, for example, big L. Let's make it big L. Okay. If I make it longer than L, would the resistance increases or decreases? It will increase, right? I mean, you have more. Think of resistance like friction. So the longer the path, the more the resistance, the more the friction. So here we have the resistance is proportional to the length. More length, more resistance. Makes sense, right? Okay. What about if I make it wider? In other words, if I increase the cross-sectional area. Okay. So how does that? Well, if I increase the cross-sectional area, that means I can accommodate more electrons. Okay, or those electrons that are here, they have more room, right? So they will flow easier. So that means it is inversely proportional to the cross-sectional area. So R here is inversely proportional to the cross-sectional area. Let me combine those two together. So the resistance is proportional to L over A. Is that right? So in this case, if I make this proportionality notation equality, so it becomes R is equal to a constant. We're going to call it rho L over A. Okay? And that's an important formula where rho here is, we call it the resistivity coefficient. Okay, and there is a tabulated value for it. I'll show it to you here. It's on page 753. Let me go there. Section 4. I don't know where I am here. This is section what? Discharging capacity. Oh, okay. We're still. Oh, this is section 1. I need to go to. Oh, I can just get it from here. 1 second. 27. Section 4. There we go. There we go. I want to just show you the table right here. Here's the table right there. So here we have the material that we're dealing with: aluminum, copper, gold, iron. As you notice here, they're all conductors: iron, silver, tungsten, nichrome, and carbon. Of course, carbon is not a very good conductor. And then here is the resistivity. Here we have a conductivity. I'll talk about it in a sec. But resistivity is right there. So for example, look at all the conductors are 10 to the power negative 8, negative 8, negative 8. Okay? So aluminum 2.8, negative 8. Copper 1.7, gold 2.4, and so on. So they have a very tiny, small resistivity. You got that? They're very good conductors, but they are very bad resistors. You got it? And conductivity, believe it or not, is basically the reciprocal of it. So all you need to do is take this number, divide it by 1, 1 over this number, you'll get the conductivity. We're not studying conductivity much. So, but this is how you get conductivity, which is the symbol sigma right there. Okay, there we go, it's right here. Well, resistivity, rho, is equal to the reciprocal of the conductivity. It's called conductivity, should be called somewhere here, conductivity. I can't see it. Oh, well, it's on the table, right? Okay, so it's basically just the reciprocal of it. We're not going to deal with it too much, but anyway, here they are. Okay, as you can see here, the conductivity of, the resistivity of carbon is not that small, if you will, compared, say, to copper or aluminum or something. Okay. All right. So resistivity is a property of the material, just like when we say the density or specific heat of a specific material. Well, part of that material, one of those unique number that distinguishes a certain material from the other, is also the resistivity coefficient or the conductivity coefficient. You got that? Okay. So that's the formula we have now. Okay. Let me show you a quick example. Again, a simple example on that. I don't think it's from the book. I have a stereo speaker that connects. It kind of stops, connects. There we go. Connects to two wires. Two wires. Connects to two wires. 20 meters each. All right. I have A and B. Here, the first question: what is the diameter? Oh, sorry, what diameter of copper wire you should be used to keep resistance below 0.1 ohm. Okay? And part B, if the current in each speaker is 4 amp, okay, we have the current is that. What is the potential difference? Basically, what is the voltage in this case? Okay. So let's see what's given. So what's given to us is that the length is 20 meters, this very long wire, and I want to know, he's asking for what diameter. Well, let me get the cross-sectional area first, right? So here's a wire, think of it like that. The length of this wire is 20 meters. He's asking for the diameter. So let me get the cross-sectional area here. I know that. Excuse me. I know that R is equal to rho L over A. That tells me that A is equal to rho L over R, correct? All right, so here we have A is equal to rho. I'm going to go back to the table. And we said copper. Whoops, what am I doing? Current, what am I? Here, sorry. And I go to the table and I look up copper. It's 1.7 times 10 to the negative 8 right there. Okay, guys? And so I go 1.7 times 10 to the 1.7 times 10 to the negative 8. And by the way, when you are doing homework or quizzes, always use the table in the book. For example, this example, I got it from another book. He doesn't use 1.7, he uses 1.68. Okay, that's another textbook. So make sure that, don't look it up on the web and expect that the same number matches the table. So if you're using if you're going to be working on the mastering physics or quizzes or homework, always use the table that you see on the book. Okay, so we have that. Multiply this by then the length is 20 meters, and then divided by 0.1. He gives it to us as well, and then we calculate that, and it turned out to be 3.4 times 10 to the negative 6 meters squared. And then of course A equals pi r squared, and then will give us this r will be, you know how to do that. The radius in this case 1.04 times 10 to the negative 4, which is 1.04 millimeter. Okay, I'm copying from my notes. Okay, and then the second part B, this is part A, and part B, he said, what's the voltage? So the voltage, we know that it is IR, and he gives us I, so just 4 amps, multiply this by 0.1 ohm, and that gives us 0.4 volt, and that's it. Okay, simple. All right, the last topic that I want to talk about is power. And I think you studied power in mechanics, and if you remember, power is work over time. This is what you have been told, which is correct, of course. As a matter of fact, you can think of it like power is energy over time, any kind of energy. If you've taken a course in thermodynamics, they'll tell you heat over time because it's energy. If you've taken a course in mechanics, they'll tell you work over time or kinetic energy over time, whatever. If you're taking, when you are taking electricity and magnetism, so we say that electric energy over time, okay? But it is always, so power here is basically the rate of dissipation of energy. That's really the meaning of it as far as electricity, the science of electricity is concerned. The rate, this is a very important word, because rate here, because it's over time. So the rate of dissipation of the energy. What does that mean? Let's say I buy a light bulb, okay? Let's say I have a light bulb that I bought from Walmart, and it is 75 watt. What does that mean? Well, let's see. You have the power is equal to energy over time, which means the unit of it is what? Energy is joule per second. See what I'm saying? So what that means as far as the light bulb is concerned, well, first of all, the joule per second here has a unit by its own. It has a name to it. We call it the watt. So the watt is nothing but joule per second. Got it? That's the meaning of it. Okay. So if I buy a light bulb and it said 75 watt, that means this light bulb is giving off 75 joules of energy every second. That's the meaning of it. Okay. If I have a 35 watt light bulb, it's giving off 35 joules every second, and so on. You got it? So it is dissipation. It is the expenditure, or you are using up the electric energy that is stored somewhere and to light up your room, for example. So it is dissipation. Okay? So energy used per unit time. You got it? Okay. What I want to do, I want to develop an expression for it, for our case here. So since we said that power is energy over time, well, energy, if you remember, U, let's call it U over T, and this is electric energy. If you remember, it is Q delta V, right? Over time. Is that right? And what is Q over T? Q over T is current. Remember, we defined current to be Q over T, right? Just a few minutes ago. So that's basically IV. So power is really IV. That's one expression for as far as for our subject is concerned. Well, we know that Ohm's law says V equals IR, So therefore, power is equal to I squared R. That's another expression. And if I want to eliminate I, for example, this I is equal to V over R. So therefore, power, I can go back to that. I'm going to eliminate the I, so that's going to be V squared over R. So these are the three expressions that you have available for to calculate power. Whichever you pick, it doesn't matter. But those are the ones that allow you to calculate power. Again, the unit of it is always the watts. It doesn't matter whether in mechanics or even in heat, thermodynamics, it's the same thing. You got it? Okay. Let's have an example. Here's an example that is related to one of the homework problems. It says it is the subject of it is electric heater. I'm not going to write it down because it takes too long. It says heater, so we have a heater here, draws a steady current of 15 amp, okay, on a 120 volt line. Okay, so they have a heater that draws a current of 15 amp, and the voltage in the across the heater is 120 volt. The question is, how much power does it require? That's the first question. Okay, I'll come back to the second question. Let's do this one. How much power does it require? Well, okay, we know that power. Let's pick one of those that we have in here. Which one? So we are given V and we are given I. So I'm going to go with this one. Is that okay? Right there. So power is equal to IV. So I is 15 times 120, and that would give me 1,800 watt. Okay, so that means, what does that mean? It means 1,800 joules per second. So you get this heater is consuming or dissipating 1,800 joules every second. That's a lot of heat. That's a lot of energy consumption. But anyway, there it is. Okay, that's the first part. The second part is more interesting. He says, how much does it cost to operate it for 3 hours per day if the electric company charges 9.22, sorry, how do I do this? Erase that thing. Put it back on the pen. 9.2 cents per kilowatt hour. Okay, this is an interesting unit. Maybe you've never seen it before. You've heard of it, I'm sure. Okay, so he said, how much does it cost money-wise? How much does it cost to operate it for 3 hours per day if the electric company charges you 9.2 cents per kilowatt hour? First thing we need to do, I want to calculate the kilowatt hours, the total kilowatt hour. Okay, so we know that the power that I am using for that heater is 1,800, the power that the heater is using rather, is that. I should just keep it in watt. 1,800 watt. Okay, now kilowatt, well, let's convert it to kilowatt. So the power, remember, I want to match this kilowatt hour first. So the kilowatt, kW, that would be what? 1.8 kilowatt. Is that okay so far? Now, kilowatt hour, that means you multiply it by hour. Okay, you multiply it by hour. So in this case, the kilowatt hour, as a matter of fact, here's a better way of doing it, is if I have 1.8 kilowatt, let me do kilowatt hour, and then I'm using 3 hours per day. And of course, the company charges me this much, and I get the bill every once a month. Is that right? So how many hours, let me ask this question, how many hours per month? That's what I'm saying. Well, it's 3 hours per day, so that makes it 3 hours per day times 30 days. Is that right? And that will be 90 hours, right? So 90 hours per month. So kilowatt hour, so all I need to do is to take that 1.8, forget about that for a minute. So I have 1.8 kilowatt, multiply this by 90 hours, and then those for every kilowatt hour, this is the kilowatt hour there, the company is charging me 9.2 cents, which is what in dollars, 0.092 dollars per kilowatt hour. Do that make sense? There we go. That's the total cost that I'm going to be paying for this heater. Make sense, guys? So we use the calculator, 1.8. Again, don't keep the kilo there. And I mean, basically the kilowatt will cancel out here. Hours and hours will cancel out. You're basically left with money. So 1.8 times 0.092 times 90, right? And when you calculate that, it turns out that it is $15. Got it? Okay, good. Okay, I want to go to the homework. I'm going to do a couple of problems before I finish off. I think I'm basically, this is what the chapter is all about. Okay, so I'm going to go to the back of the chapter, that is, and I'm going to do, sorry, let me start with number 40. I'm going to do number 40 and 43. How about that? These are both homework. I think I have them marked as homework. So, okay, let's do number 40. Okay. Oh, maybe I should go with I'll show you in the book where they are. There we go. Number 40, right there. Okay, we got to do 40 and 43 about the sculptor. There we go. Okay. So maybe I should take this one out just for the sake of giving you more space to see. There we go. Okay. I can move it here. Okay, it says an electron beam. There we go. Right here. Number 40. It says an electron beam inside an old television picture tube is 0.4 millimeter in diameter and carries a current of 50 microamp. Okay? This electron beam impinges on the inside of the picture tube screen. Okay, let me write that down, the data. Whoop, there we go. So I have an electron beam, and I have we have a diameter 2r of I'm going to read it from my hard copy here, 0.4 millimeter, and in diameter, and carries a current I equals to 50 microamp. Okay, This electron beam impinges on the inside of the, okay. Now, first part of the problem, he says, oh, how many electrons strike the screen each second? Okay, so here is a little picture for you. Imagine here is the tube, here is the screen right here. So the electron coming out of the tube like that. At least that's how I'm picturing it. And here's the screen, the inside of the screen. So the electron is striking it, okay, like that. And I want to know how many electrons strike the screen each second. Okay, how do we do it? Well, we know that the current I is equal to Q over T, right? And then Q, what I'm doing here, I want to develop an expression, and then I'll explain it. Q here is E times the number of electron, correct? You know, the charge is equal to the fundamental charge times the number of electrons divided by delta E, okay? Now, if I take N over T, N sub E over delta T, that's equal to, I can move the E here, that's equal to the current divided by E. Is that okay? Remember, what did he says? He says, how many electrons strike each second? Well, here it is. Number of electrons each second is equal to what? Current over E. Do you see the trick? Okay. And it's given to me, the current. The current, he says, 50 micro. That's 50 times 10 to the negative 6 amp divided by the fundamental charge. And then I would calculate that. And I have already calculated this one, and it's equal to 3.1 times 10 to the power of 14 electrons per second. Okay, that's how many electrons are striking the picture tube from the back here every second. 10, it's not clear, I'm sorry. Let me write it better. Okay, makes sense, everyone? Okay. The second part, there are four parts. What is the current density in the electron beam? What's the current density? Well, the current density, which is J, I didn't talk too much about it, but basically it is I over A. It's the current per area, okay? And the area here is pi r squared. So that means the current density would be, I mean, here, the area right here, right? So the current density would be 50 times 10 to the negative 6 divided by pi r squared. We already have the r, the diameter. So r is just 0.2 millimeter. You work it out. No need for those details. So basically, when you work it out, it's 4 times 10 to the second amp per meter squared. That's the current density. You got that? Easy? All right. And then part C, he says, the electrons move with velocity 4 times 10 to the 7. Now, this is definitely not the drift velocity. Remember, drift velocity only for electron moving through a wire. These electrons are moving through the vacuum tube here, from here to here. So they're moving with a very large velocity v here. These are not drift velocity, okay? It's equal to, so now he's saying, okay, you got the electrons move with a velocity of 4 times 10 to the 7. That's pretty close to the speed of light, right? What electric field strength is needed to accelerate the electron from rest to this velocity in a distance of 5 millimeters, okay? So here we have, think of it like, here is the distance of 5 millimeters from here to here. Okay, the electrons come out with a speed of v naught. I'm sorry, no, I'm wrong. They come out with a zero speed. V naught is 0, and then they reach the velocity here of that number that is given to us. You know, whatever. Okay. So he's asking, what is the electric field here? The electric field strength here. Got it? Let me draw a better picture. Here is the screen. Let's make it flat. Here is the electron beam here. Here's the electron coming out. They're starting with initial velocity 0. Okay? So they come out, they accelerate through, and because the electrons are negative, so that should be, let's assume this is positive, so they're accelerating through it. Okay? So there is an electric field here, this way, if you will, right? And the electron, this electric field, and the electron, he'll take one electron here, is moving like that. By the time it reaches here, it says that the velocity of this electron is what's given to us, 4.7, right? So it's equal to 4 times 10 to the 7. Now, he wants to know what is the intensity of the electric field, okay? Now, this one is a simple kinematic problem, if you haven't thought about it yet. Basically, let me use the second kinematic. V squared equals V naught squared plus 2ax, x being the distance from here to there. The initial velocity is 0, so basically V squared equals 2ax. And he's asking for the for the electric field. Well, okay, I don't know the acceleration. I know x and I know v, but I know that F equals ma. I mean, what's causing the electrons to move from here to here is a Coulombic effect. So the acceleration is given by that, is F equals ma. So, but F here is the Coulombic force, and it is also equal to what? EE, remember? ma, so therefore A is equal to EE over m, m being the mass of the electron. Now plug it back in there. So I have here V squared equals to 2EE over m, did I miss something? 2x, right, there we go. So therefore, lift it up. Therefore, I'm solving for E is equal to mv squared over 2ex, and that's it. There we go. That's the strength of the electric field. I just only need to plug in the values. This is the mass of the electron, 9.11 times 10 to the negative 31. The velocity given to us, 4 times 10 to the 7 squared. Is that right? Yes. Divided by 2 times the fundamental charge times the distance. He said what? 5 millimeters? 5 millimeters, right? So it's equal to 5 times 10 to the negative 3. And then you go through all that calculation. I have done it already. And if I didn't make a mistake, it's 9.1 times 10 to the 5th volt per meter. There we go. This is the strength that is inside that picture tube. Got it? Okay. The last part, which is kind of the most abstract, part D, he says each electron transfers kinetic energy to the picture tube screen upon impact. What is the power delivered to the screen by the electron beam? Okay, so the first thing that comes to mind when you hear the word power is what? Energy over time. All right, and he says kinetic energy, so basically we're going to do kinetic energy 1/2 mv squared over time. I already know what the velocity is. He gives it to me in part C. This is the mass of the electron, and this is the time. Okay, now this is power for one electron, but I want to know all the electrons per second. Okay, well, how many electrons per second? Well, here it is. Oops, sorry. It's right here from part A. We calculated the number of electrons per second, remember? Here it is. Remember part A? He says how many electrons strike each second. Well, there it is right there. N over T, right? 3.1 times 10 to the 14. So now, the power for all electrons is 1/2 mv squared times n sub e over t. T for 1 second, that is. This t is 1 sec only. So I have 1/2 times the mass of the electron. 9.11 negative 31 times the velocity, 4 times 10 to the 7 squared, times the total number of electrons. It's over there. What is it? 3.114. 3.1 times 10 to the 14, and then we calculate all that. So the power delivered is equal to, if you do all that calculation, 0.23 watt. Got it? This is kind of the toughest part that you want to, it's not very tough, but it is, you want to pay attention to this part, how it was calculated. And it's all based on the concept that the power is energy over time. Got it? Okay, the last problem, which is kind of short, and that is number 43, and then we'll call it a day here. I think I covered everything in the course, in the chapter. So 43, let me switch to 43. It says, a sculptor, let's read it together. He says a sculptor has asked you to help electroplate gold onto a brass statue. So I have a brass statue and I'm going to electroplate it, basically paint it with gold. You know that the charge carriers in the ionic solution of the gold, that is, are singly charged. What does that mean? It means E is, it's basically 1E. You see what I'm saying? E, not 2E or 3E, singly charged. Those ion has a charge of E. Okay. And you have calculated that you must deposit 0.5 gram of gold to reach the necessary thickness. So you only have 0.5 gram of gold. That's mass. How much current do you need in milliamp to plate the statue in 3 hours? Okay, so all right, let's write down what the data is. So I have the mass is 0.5 gram. You would think it's more for a statue, but anyway. And then what else do we have? Seconds. And it's singly charged. Okay, how much current? So he wants the current to in 3 hours. So we have the time, 3 hours, which is basically 3 times 3,600. Let me just calculate that very quickly. 3 times 3,600. It is 10800 seconds. Okay. All right, and he wants the current. Okay. So the first thing I need to know is how many ions, or how many atoms rather, how many atoms of gold are in this half a gram of it. How many atoms or ions, atoms of gold in 0.5 gram? Okay, well, I use the go back to chemistry. I know that N, the number, those number of atoms over Avogadro's number, it gives me the mass that is given to me, the mass of the sample, which is this one, divided by the atomic mass of gold. I looked it up already for you. It's 197. So we have 197 gram per mole. Okay, so basically, if I work it out, so that's N, this N right here, is equal to the mass M right there, times Avogadro's number, over 197. Okay, and then we just calculate that. So I have 0.5 gram divided by 197 gram. I don't need to convert. They're gonna cancel out. Times Avogadro's number. What's Avogadro's number? I forgot. Look it up. Avogadro's number 6.02 times 10 to the 23, and then we calculate how many atoms are there. It is 1.53 times 10 to the 21 atoms, or ions, whatever you want to call them. Okay, got it so far? Okay, now each atom is really an ion, which means the charge on it is E. You see what I'm saying? So the total charge Q, let's call it Q, is equal to En. Make sense? So we have the fundamental charge, 1.602 times 10 to the negative 19, divided by N that I have got, is this one right there, 1.53 times 10 to the 21. So the total charge is 245.1 coulomb. That's the charge. Why do I want the charge? Well, I forgot to mention, I know that I is equal to Q over T. So I want to get Q. There it is. I got the Q. He said, how much current in 3 hours, right? How much current in 3 hours? So all you need to do is divide the. Did I do it right? Hold on, I'm sorry. Yes. So what you want to do, you want to calculate the current, which basically the charge, which is 245.1, divided by the time is 10800 seconds. You calculate that, and it turned out to be 0.0227 M, or the current is equal to roughly 23 milliamp. And there we go. You got it, guys? I think I'm okay. So I think I'm going to stop here. Let me know if you have any questions, and have a wonderful day. Bye-bye.